So I'm going to cover with you all today the updates and changes to the Vermont Residential Building Energy Standard. We have some significant changes that came into play from the 2015 to the 2020 code. So we're going to cover that and kind of focus the content here towards prescriptive compliance, as prescriptive compliance is kind of what the code is essentially built upon, and a lot of the content and data associated with it is built upon that as well. So navigating through some weird things here. So getting going here, this is the content of the session today is owned and copyrighted by the ICC, which is the International Code Council. The ICC is the publisher of the code. So more information about the code can be found through their website, and a lot of the references that we're going to be using here today in regard to the content come from the ICC and are copyrighted by the ICC. So just as a background to the code, the Vermont Residential Building Energy Standard became a law as an act of legislation in 1997. So it's been around for a while, and it is typically a 3-year revision cycle that goes through public process and is led by the Department of Public Service. It's based on the International Energy Conservation Code, the IECC, which pretty much every state in the U.S. follows the ICC and adopts the language for their specific state and climate. So that is Vermont's way of using the code as well. The 2020 RBES came into effect on September 1st of 2020. So any projects that have broken ground and begun from September 1st of 2020 on need to meet the 2020 code, and any projects that got underway prior to September 1st need to meet the 2015 code. So some of the major changes for 2020. There are some new insulation requirements and packages. Packages plus points is a new thing. There's points requirements based on the size of the house. So that's what we're going to kind of base a lot of the content here around today. Options and requirements for ventilations that are a little bit different. Blower door testing is now required as building envelope verification on project completion. Some clarifications in use of electric resistance heat and prohibitions of use of electric resistance heat. Electrical vehicle charging infrastructure comes into play for stretch code and multifamily projects, as well as solar ready components coming into play for stretch code. And at the outset here too, I want to make a distinction for everyone in regard to the code and the code handbook. Efficiency Vermont, in partnership with the Department of Public Service, publishes the Vermont RBES handbook, which is essentially a guide to the full code. Again, the ICC published code is the full language of the code. It contains all of the relevant rules, regulations, and guidelines to comply completely and effectively with the code. And the handbook is essentially just a summary guide with a lot of actual details in it to help people comply with the code. So the handbook should not be used as a substitute for the full RBES. So just that's a distinction to be aware of. And you'll see here where you can find access to the two different documents. So again, the ICC and their website is where you can find the full language of the code, and on the Department of Public Service website is where you can find the handbook, and also you have a link there as well to the ICC site. And then Efficiency Vermont's role in all this is we serve essentially as the state's Energy Code Assistance Center. So we provide training, support, questions and answers, code support for implementation and application of the code. So you can reach us at this number here, our office address, and you'll be connected with one of our customer service teams and/or myself or another energy consultant to answer any questions that you may have about the code. And again, the Vermont Department of Public Service is the quote-unquote owner of the code, so they can also be reached with any specific questions. So we'll start off with buildings that comply. So the RBES, the Residential Building Energy Standard, applies to residential, low-rise, new construction, and existing homes. So 1-, 2-family dwellings, multifamily that's 3 stories or less. It does not include commercial. So if you do have a mixed-use building where you have commercial space at street level and then residential units above, commercial would apply, and the commercial code would apply to the retail space, commercial space, and residential RBs would apply to the residential portions. Existing homes also fall under the code as well. So additions to an existing home need to meet the requirements of new construction, essentially for code, and renovations, alterations, repairs have their own requirements that are defined in Chapter 5 of the code. Any projects that require an Act 250 permit, so this is typically for developments, those projects need to meet a more stringent code standard, which is the stretch code, which we'll touch on today and not go into too much detail, but stretch code basically requires that you go to a higher level of performance than what the base code requires. Stretch code can also be adopted by a town or municipality as the local code requirement and hold projects to be meeting a higher level of performance in the individual towns. So far in Vermont, South Burlington is the only municipality that has fully adopted stretch code as their local code requirement. There are exemptions in the code, and they're pretty specific in their exemptions. Low energy use buildings, which really don't apply to, that was something that's a kind of a legacy thing in the code from previous versions, which doesn't really apply now, but there is a carve out for that if you want to look at that more specifically. Unconditioned buildings, so a garage that's separate from the house, unheated, an outbuilding, if it's not a residential use, it doesn't need to comply. Mobile homes have their own federal standards. Hunting camps / summer camps that aren't year-round buildings, aren't residential buildings, those are exempt. Yurts, if you're into that kind of thing, those are exempt as well. And then there's specific exemptions for owner-built homes. So the owner-built exemption is pretty specific in its application. In order for someone to use the owner-builder exemption to comply with the code, meaning that you don't have to fully comply with all the requirements of the code, you need to be an owner builder building the house for yourself. You're actually serving as the general contractor and detailing all of the construction specifications for the house. And you do need to disclose in writing what those differences are in the building specification from what code requires that you have built, and that needs to be disclosed in the code certificate. Existing buildings, additions, and renovations, repairs, these are covered in Chapter 5 of the code. So additions and alterations need to comply. Additions in and of themselves as a new construction component to the building. But if you are altering a building, then if you're changing from unconditioned space to conditioned space, let's say you're finishing a second floor of the house in a cape that was previously just attic and you're turning it into living space, then you need to make that portion of the house that you're changing meet the requirements of for new construction. If you're insulating a house, the intention is to meet the new construction code requirements for insulation. And if you can't, you need to at least be filling the cavities fully with insulation. Replacement windows, if you're fully replacing a window in a house, not just replacing the glass and the sash or putting in a storm window, but you're actually replacing the whole unit, you need to meet the new construction requirements for windows. And there are exemptions, so if you're working on one part of the house, you don't need to bring the rest of the house into compliance. Storm windows, as I said, glass-only replacements don't need to meet the requirements. Again, existing building cavities, walls, ceilings, floors, etc., if they're full of insulation already, then they don't need to come up to new R-value requirements. So there are some exemptions that come into play in existing homes. Then finally, liability. The way the code is structured here in Vermont is this is a self-complying, self-reporting code. There are no code officials in the state of Vermont. Efficiency Vermont does not have any role in code enforcement. So it is up to the builder or the person certifying and signing the code certificate that the building complies with the code. The homeowner has recourse to take against the builder or the person certifying that the home is compliant. They can take civil action and recover damages for to bring the building into compliance for damages that could occur because of non-compliance, et cetera. Those claims need to be filed within 6 years, and that's specific to a claim under RBES non-compliance. It doesn't mean that a builder or general contractor could not be held liable for other damages that may incur over time, but it wouldn't be a specific RBES related claim. And there's more awareness now of code that it exists and that it is a factor and should be verified in any new construction or major renovation addition project in the state. And more lenders and title attorneys and the real estate and lending industry is becoming more aware of this and expecting to see documentation associated with homes. So any questions before we jump into more of the details about the code and general requirements?
Feel free to either raise your hand or just type questions in the chat box.
Yeah, great. Okay, general requirements. The code is basically designed as a construction reference document. So it really is designed to be used as a reference point when you're coming up with the design and specifications for the building. So the way that the code is actually laid out in chapters, it kind of follows that process of design and specification. So first couple chapters in the code, and this is referring again to the ICC published document, cover the scope, administration, and general definitions for the building. Actually, I'm just going to go through the slides ahead, which kind of define these things. So chapter 1 kind of covers what we just went through as far as how the code applies. Chapter 2 is a list of basically a glossary of terms, definitions for terms that you're going to find in the code, and specific definitions of what some of those terms mean and apply to. Chapter 3 is general requirements. So basically, this is defining building load design conditions, what you're using as references for specification for insulation materials, building systems, equipment, HVAC, ventilation, etc. Chapter 4 is really kind of the heart of the code, the meat of the code, which contains all of the energy efficiency related requirements. So we're talking the relevant R values, window values, air sealing requirements, ventilation and mechanical equipment installation requirements, etc. So that is kind of the bulk of the content of the code and what we're going to focus on today. Chapter 5 specifically covers the requirements for existing homes and gets into some of the nuances of how that works. And then finally, Chapter 6 is reference standards. So these are industry-related standards and other codes that overlap with the energy code and are a part of the overall code purview when it comes to residential construction. So again, we're going to dive now into the details, kind of getting into Chapter 4. So you can see this is referencing Section 4, so R4. So this means Chapter 4. If you're going to follow up on some of the content here after the training, the sections that I'm calling out here in the slides reference these sections within the code document itself, the ICC code document. So there are 3 different pathways to comply with the code. The prescriptive method is essentially you're picking a package out of a table of 5 different packages where that package contains different performance specifications for different building components. So you can choose a package to follow and meet all of the specifications in that package and then follow the other general code requirements that'll overlap with that and comply to the code that way. Alternately, you can use ResCheck software, which is an online web-based modeling tool that allows you to kind of substitute higher values for lesser values in certain areas of the building. So it provides a little bit higher level of flexibility. And then finally, similar to that is the home energy rating method, or the HERS rating, where you're actually working with a third party to do the building verification for you. And similar to the res check method, it offers some more flexibility in regard to kind of moving around the component requirements within the building. But again, we're going to focus today on a lot of the content related to the prescriptive packages, because the prescriptive packages and the specifications called out in that are anchored to those other two prescriptive methods, the res check and HERS rating method. You still have to kind of meet kind of what the base requirements of the prescriptive method calls for to use those other two options as well. So prescriptive packages, they're pretty simple, straightforward way to comply with the code. You don't have to do building modeling. You don't have to come up with area and volume, components and look at weighted U values across the building. So it can be pretty straightforward way of complying with the code. It is limited in its flexibility. And there may be some components of the building envelope that may be hard to achieve based on the building design. But the way that this is functioned, again, is like I said, there's 5 packages here to choose from. So this is table R402121 in the code. And this is the table that you would be referencing to choose a package to comply with. Log homes have their own package here, so they're special unicorns in their own right. So you have a separate code to reference if you're building a log home. The reason being is that a log home is built out of just that, logs, and it's entirely different in performance than a building that's built out of dimensional lumber, and you have building cavities to fill with insulation. So those prescriptive packages you're essentially dealing with for a standard stick-built construction are going to be these 4 packages here. So, you're laying out different building component R values, ceiling, walls, foundation walls, windows, etc. And what you're looking at here is picking one of these 4 packages to comply with. Package 4, package 1 are kind of the two, sorry for PowerPoint getting ahead of me on this. Package 1 and package 4 are kind of the 2 most common building envelope packages people will orient towards, because what this is showing here is R20 cavity for a wood framed wall. So this means your standard above grade framed wall. This is a package where you can build a wall with just insulation in the wall cavity and be compliant with code. Code is moving in the direction of requiring continuous insulation of some type on above grade walls. So that means that instead of just having insulation in the stud bay, you're now adding some element of continuous insulation that's cutting off the heat loss and conductivity between the studs and the framing members in the wall itself. So that is a big distinction to be aware of here, where in package 4, you can see for wood framed walls, it says R20 cavity. We jump over here to package 1, you're going to see this R20 plus 5 or 13 plus 10. So what this means is that R20 in the cavity, so this would be a standard 2x6 wall with insulation filling the wall cavity, plus 5 means that you're adding R5 of continuous insulation either on the outside of that wall or the inside of that wall to get a continuous insulation barrier as well. Alternatively, this package allows to do a 2x4 wall instead of 2x6 and fill that wall cavity, that stud bay, with insulation, and then add R10 of insulation. Jumping over to package 3, same approach, but we're going to higher R values here, where you've got a 2x6 wall, insulation in the stud bay, and then adding R12 of continuous insulation. So what to be aware of in this is that when you're choosing a package to work with, you're picking a package and you're meeting all of the requirements in that column. You can't pick the attic values from package 4 and then do the wall values for package 2 and then do the floor value for package 3. You have to follow all of the components in the single column, the single package. The prescriptive package has been around from pretty much the beginning as a way to comply with code. And a significant change for 2020 is now you, as well as meeting the specific requirements called out in those packages, based on the square footage of the house, you're going to need to gain points from a points table, which is going to follow here, which is essentially raising the performance values in parts of the building at your discretion to attain the required points here based on the square footages. So focusing on the single family residential here, if you have a building that's less than 2,000 square feet, you need to meet all of those package requirements. PowerPoint, slow down, please. And then gain 5 points. If the house is between 2,000 and 4,000 square feet, you need to gain 7 points. Anything greater than 4,000 square feet, you need to gain 10 points. So what this means is then in the code, as well as that table that shows you the packages to follow, there is then this table which gives you points options for different parts of the building where you can attain points. So if you choose package 4 and you're doing, that's a cavity only above grade wall package where you can do R20 in a stud bay and comply with the code. If you need to gain points, you can go to this table and choose to do continuous insulation of some type and earn points by doing so. So you can add R12 of continuous insulation to that R20 wall and gain 2 points. You can go to an even higher performing wall and gain 3 points. You can up the ante in the attic for insulation. You can go from R60 to R80 and gain a point. You can install better windows than the minimum of what's called out in the package and gain some points. There's also avenues for making the building envelope tighter and gaining points there. Going from exhaust-only ventilation, which is allowed in the base code, which means just using bath fans on controls as your mechanical ventilation requirement for the house, which we'll go into more detail later. You can swap from that to a balanced heat recovery ventilation system and gain points there. You can put in higher performing heating and cooling equipment. You can put in higher performing domestic hot water heaters as well. And there's ways to gain points focusing on water use here in the code as well. So this is a significant change from the previous versions and something to be aware of as you're going through the options for how you want to comply with the code. Any questions at this point? Okay, we'll keep the ball rolling here. Jumping ahead to stretch code. So stretch code, as I mentioned at the beginning, if it's an Act 250 permitted project, or if you are building a house in South Burlington, you need to meet a higher level of performance, which is stretch code. So stretch code has packages as well, but you'll see here that it's a higher level of performance. If you need to meet stretch code, then you can no longer build a cavity-only insulated wall. You need to be doing a continuous insulation wall assembly of some type. You're also required with stretch code to be using balanced heat recovery ventilation instead of exhaust-only ventilation. The window values are a little bit higher or lower, depending on how you want to define it. So there is some performance bumps that you need to take to meet stretch code. Similarly, though, or the same as well, with base code, you still have a points requirement here based on square footage, and you can see that the points are, to be attained are even higher. So you have a little bit higher threshold to meet in regard to points. So you do need to still meet. There are a lot of other requirements called out in the code in Chapter 4 as far as installation requirements and other air sealing details, etc., which we're going to touch on here in a moment. All of those requirements need to be met if you're needing to follow stretch code as well. And you only have 2 options to comply with stretch code instead of 3. So you can use the packages approach, the prescriptive package we just showed here, or you can have a HERS rating done. You do not have the option of using res check to comply with stretch code. So jumping back into base code requirements here. As an alternative to doing the prescriptive packages, you can use a weighted U value or U factor approach to comply with the code. So this is essentially as an alternative to doing the prescriptive tables. If you want to use res check as your compliance method, what you're doing is you're instead of looking at R values in building cavities, you're looking at the overall performance of an assembly by doing a UA or U factor calculation as an alternative to complying with the prescriptive R values in the code. The ResCheck software does that modeling for you, and it is an option. Though in order to use ResCheck, you do need to up the ante in a couple places, which is you need to make the building envelope tighter, and you need to have a much a tighter air sealing strategy and envelope to use the ResCheck or UA alternative. And again, you need to go from exhaust only ventilation to a balanced heat recovery system if you're going to use the ResCheck or UA approach. So just briefly to touch on what this means is that, as I'm mentioning here, R values are basically the resistance of a material to heat flow. U value is basically how well a material conducts heat. So they're an inverse of each other. So when you're actually doing a U factor or UA value for a building, you're accounting for the entire assembly of that area that you're looking at. So that means you're accounting for not just the performance of the insulation in the cavity of the wall or the roof, but you're accounting for how much conductivity of heat gain or heat loss is occurring through the framing materials as well. And that goes into a broader calculation, which gives you the U value assembly. So again, this is what ResCheck, the tool itself, does. These are the thresholds in the code when you're doing those UA or U factor weighted assemblies. So again, these factors here, instead of it being an R value, it's a U value, and these U values are taking into account the overall performance of the assembly, including all of the framing in that wall or roof or floor as well. Any questions on that? Okay, keep the fire hose going here. Some notable alternatives, exemption or exceptions in the code. There are a few things that are called out in Chapter 4. Again, as I said, Chapter 4 is kind of the meat of the code, which gets into all of the real details of the building envelope and R values and installation requirements for those areas. So R49 for an attic, an open attic, is kind of a standard base R value for any of the packages. There is an exemption or allowance in the code to use R38 in place of R49 if that R48 covers 100% of the ceiling area. So essentially what this means is that at the eave and at the exterior wall dimension, you can have full height of insulation to achieve R38. And you can carry R38 across the whole ceiling flat and make that, that would be seen as equivalent to R49. Whereas, more typically without a raised heel truss like this, you have reduced R values at the eave because of the diminishing height of the roof rafters coming down to the exterior walls. Alternatively, where the code requires R60 in a ceiling flat, again, you can comply with that with R49 with the same performance specification here, that you're getting full height of R49 all the way out over the top plates of the exterior walls. Carrying on this theme, some more specific insulation requirements. So there's a table and there's more specific detail in the code, which basically gets into the more definitions and delineations around how to properly install insulation materials and air barrier materials and vapor control layers within the building envelope. So it's not as easy as just saying I've got an R42 or an R30, whatever in the building. There are specific requirements on how those materials are installed and how they behave together. Just to put it out there, any building assembly is a system of parts and components and pieces. It's like a giant Lego set, and you got to make sure that all of those parts and components and pieces are interacting appropriately together and behaving well together. So that is the reason why there are these types of call outs in the code, to make sure that those proper alignments occur when putting the building together. So one of the bigger things to be aware of in this section is unvented roof assemblies. So these are basically cathedral ceilings, vaulted ceilings. There are some concerns about different approaches to take when you're putting that sort of closed cavity together. So there are specific options in the code that are called out about how to put together a cathedral / vaulted / unvented roof assembly. So it can be air impermeable, meaning that the insulation material put into the rafter bay will not allow air to move through it. That's an air barrier type insulation. Alternatively, air permeable insulation only can be used in the cavity with some additional built up continuous insulation on the roof above it. And then alternatively, third option is to be a blend of those two, where in the rafter bay you have a mix of air impermeable and air permeable insulation. This is kind of referred to as like a flash and bat assembly. So here's some visual examples of this. So the option A, air impermeable insulation, you're basically putting spray foam into that cavity to meet closed cell spray foam specifically. In that cavity to meet the R value requirement. If you want to use cellulose or fiberglass or mineral wool in the rafter cavity, you can do that without it being vented, as long as you have a R value of R25 effectively in continuous insulation above the roof deck to protect the roof sheathing from condensation. And then as an alternative to this pathway here, there's the flash and bat, flash and fill approach, where you're actually installing closed cell foam to get half of the R value required in the assembly, so half of R49, and spraying that against the roof deck, the roof sheathing, and then filling the balance of the cavity with cellulose insulation or blown in fiberglass, or sometimes you know, a bat of insulation, rock wool or fiberglass. Just to reiterate this in a little more detail, again, air impermeable, spray foam only. It has to be closed cell foam. It cannot be open cell, because open cell foam will allow moisture vapor through it. So essentially you're protecting the roof deck from condensation by having significant R value in the cavity and R value that does not allow moisture vapor to move through it. Alternatively, as we said, you know, cavity only insulation, or cavity insulation that is air permeable, so cellulose, fiberglass, mineral wool. You can do that without a ventilation cavity as long as you're protecting the roof sheathing here by having adequate R value of rigid foam insulation or rigid insulation of some type above that roof sheathing. So that's an alternative. And then again, the flash and fill approach, where you're putting a closed cell foam directly against a roof deck to half of the required R value, and then you're building out the balance of that with fiberglass, rock wool, cellulose, etc. Any questions on that? Sure, looks like we have a question. Evan? A couple questions popping up. Feel free, if you can unmute yourself, feel free to speak.
So I have a question.
Go ahead.
Sorry, it's for relating to fenestration. If I just, when calculating your average U value, you said total assembly, which is, I'm assuming, is center of unit as opposed to center of glass value. Can we take the average center of unit U value instead of having to do a formula using square footage of glass?
In general, overall, for fenestrations in code, you're complying by way of an overall weighted U value for all windows in the building. And the U value that you're using to evaluate that is the overall unit U value. So not center of glass, but the overall window unit U value. So the NFRC rated U value that's going to be associated with those windows is going to be what you're using. So
an average center of unit value.
Yeah, average center of, not center of glass, you know,
right.
You need to take in.
Understood.
Yeah, so, okay, yep. Cool, we're on the same page then.
Got it. All right, thank you.
Yep. And then there's another question.
Yes, this is Dennis Borbo. I had a question on your unvented attic assemblies that you just showed. Do you have a preference or a recommended better performing structure?
So out of these three here,
Yeah.
it really, no, honestly, I mean, any of these three approaches are viable and safe and durable, as long as you're specifying them appropriately. The one that can get risky would be this one right here, where if you short yourself on R value on the exterior insulation, then you can create a cold surface with the sheathing and start to get condensation there. So out of the three, you know, and the same can happen here in this assembly too, where if you skimp on the R value in the closed cell foam, then again, you can get condensation occurring on the surface of the foam here. So, you know, probably the bomb-proof approach is you're filling the cavity with closed cell foam to the appropriate R value, and you're making sure that foam's installed under the right conditions so it doesn't shrink in any way, and you know you're not putting yourself at risk of condensation on the sheathing at that point. Again, these other two approaches here can be just as equally effective and perform just as well, so long as you're taking into account that you're getting, you know, 50% of the R value in the closed cell insulation material and the other remaining 50% in the vapor open type.
And ultimately, if you have the ability to install an air vent channel, that would be even better yet.
Well, an air vent channel is going to be only really coming into play if you're using fiberglass, rock wool, mineral wool, a vapor open, a vapor permeable insulation, and you're trying to just get that R value in the rafter cavity. The trick with it right now is that any sort of cathedral or vaulted ceiling needs to meet R49 in the code. So trying to get R49 with fiberglass or rock wool or mineral wool or, you know, any fiber insulation in a 2x12 rafter and get a vent space in there is not attainable. You know, you have to go to a TJI or, you know, another type of rafter assembly to get it deep enough to be able to accommodate that R value in a fibrous insulation.
So what you're saying, if you're going to go with spray foam, the entire cavity, there's no need for an air channel.
Correct. Yep.
And the spray foam guy that I just did a house, he highly recommended a vent channel and said that the spray foam will last a lot longer and you don't get any deterioration underneath the OSB if you have a vent channel. So,
you know,
that was just an opinion, basically.
Yeah, or so. I mean, you know, the R, as long as you're getting the appropriate R value in that foam, then what you're trying to achieve here, either way that you're talking about here right now, is ensuring that the roof sheathing stays to the outdoor temperature. You don't want it getting, you know, you don't want air from within inside the building that's, you know, warm and humid coming in contact with that cold roof sheathing. So you want to isolate indoor air from that. Venting in a rafter cavity was historically put in place to kind of mix cold air and try to keep the roof deck cold from the warm and moist air that was leaking into that rafter cavity to begin with, because, you know, that was kind of before we had spray foam as a regular option for insulating rafters, or good air barrier assemblies to put in place. So, you know, if you have a foam contractor, insulation contractor who prefers to put the foam against a vent channel and they can still get that R49 in that foam in the cavity still with that vent channel in place, then that's fine. You know, that's their opinion of what they think is the best cavity assembly to do.
Okay, thank you.
Sure.
And Steve, we do have another question
Okay.
from Evan.
Yep.
Evan, if you want to unmute yourself, you can go ahead and ask.
I'm sorry, I think I forgot to put my hand down.
Oh, okay.
No, no
All
problem.
right.
All right. Well, I'm gonna move along then to some of these others.
We do, sorry, a couple more questions coming in. That's great. One from Bill Moore, if you want to unmute yourself. think you are unmuted, Bill. All right, well, let's see. Jenna, do you have a question?
Go ahead.
Yeah, this is actually, hi, Steve. It's Josh Rourke calling. How are you?
Hey, Josh. Good.
Hey,
Good to hear you.
real quick question. You mentioned that if you do the flashing bed, it has to be half the R value. Is that stated in there, or that's just the recommendation? I understand the reason for it, but I'm just curious if that's actually written in the code.
It is, I think the specific language in the code is that it's recommended.
Okay,
But
that's what I saw. That's what I saw in this book also, but I wasn't sure.
I would blur your eyes a little bit and read it as required.
Okay, I think it's a good rule of thumb anyway. I'm just curious.
Yeah. From a building science standpoint, that really stands up as the way to approach it, is to get that half that R value in place with the air.
Okay.
Great, thank you for the question. Another from Jay Graves.
Yeah, I was just thinking about the foam and the vent space above the foam that was mentioned before by the recommended by the insulation contractor, and all of this stuff you're presenting to us says that this air impermeable insulation needs to be in direct contact with the sheathing. So it seems like you would not want that vent space there.
I don't want to get too far off track from where we're going with the rest of the content here, but I mean, there's the intention to do this is to protect the roof deck from interaction with mixing with any sort of air from within inside the building. So if you're putting an airspace between, and leaving a vent channel there, and you're spraying foam directly against the material that you're using as the vent channel, and it's of adequate R value to meet the requirements for the assembly, and you don't have any other pathways for air to leak through to get to that vent channel material, then you're really just separating the you're creating like a secondary roof deck almost in that way. And there are definitely assemblies out there where you're physically separating the roof deck from the insulation cavity below it, where you're filling a rafter cavity and either sheathing it and filling that rafter cavity completely, and then putting strapping or sleepers over top of that, and then putting your actual roof deck that you're going to shingle or put metal on above it. So it's concept that you're trying to achieve really there with that is the best way I can describe it.
Yeah, I've seen the ones with a cold roof on top, and I get that. I guess I would be nervous that you could keep all the moisture out of that space if you left it on the underside of the sheathing. But I guess we probably wouldn't do it.
Yeah, I mean, the bottom line concept here to digest is keeping any air from within the conditioned part of the building from getting into that cavity and interacting with a cold surface somewhere within the cavity, keeping it away from the cold surfaces, keeping it away from the roof deck. So,
And we'll maybe take one more before we move on with content. Bill, do you want to try again?
if you're having trouble connecting to, you can always just drop a line in the chat if you have access to that.
Yeah.
Sorry, Bill.
Well, why don't we move on with content, and hopefully we can troubleshoot
Sure.
to get Bill's question in for you.
Okay. One other important requirement as well, regardless of the ceiling type, whether it's a flat open ceiling or a vaulted rafter cavity, eave baffles preventing air from the soffit and from outside of the building from interacting with the insulation that's going to be in the ceiling flat or in the rafter bay. So you need some sort of air impermeable barrier at the soffit, essentially, to keep air from mixing with this insulation. That's going to be in place. So that's a big one to attend to. Access hatches and doors. So anything going from a conditioned space to an unconditioned space needs to be essentially treated like an exterior entry door. And if you're going into an attic, the intent here is to have that hatch be insulated to an equivalent R value or close to it of the ceiling or attic assembly that it's going into. So, you know, we're talking a barrier, a baffle to retain the insulation that's in the space above it, adequate R value, typically in rigid insulation on the back of the access panel to get to an appropriate R value, and then a gasket, some sort of, you know, something to make that panel airtight when it's resting against its stop to get into the space above it. If you're going into a knee wall space, same sort of approach to be taken. Floors, if you have a cantilevered floor or a floor assembly that's going to be insulated over unconditioned space, the insulation needs to be installed in that cavity so it's in permanent contact with the floor system above. So you don't want an airspace there between the insulation and the floor deck above. So it needs to be in full contact all the way around. Again, these are not all the details that are required in the code. This is just kind of a summary of some of the high points of some of the more common details. Basement walls, foundation walls. So any conditioned basement or space that contains distribution equipment for heating of this house or conditioning of the house, the walls need to be fully insulated down to 10 feet below, to 10 feet or below grade to the basement floor, either one. So essentially you have to insulate the entire wall. The only exemption to this is if that space is truly unconditioned, then you can insulate the floor system above it. So there's not a specification in the code that requires that you insulate the inside of the foundation or the outside of the foundation. You can insulate a little bit on either side. You can frame a wall in front of the foundation. There's different ways of skinning the cat here, but pardon that, Tom, that pun. So there's different ways to achieve this. You're not bound to one way of insulating the wall versus another in the code. It just comes down to the R value requirement. That being said, if you are going to insulate the foundation from the inside and it's going to be left exposed, unfinished, then you do need to be using a rigid foam board that has a fire and ignition barrier approved facing on it as an assembly. Or if you're using spray foam insulation to insulate to the R value required for a foundation wall, that foam also needs to have a thermal ignition barrier paint or coating on it as well. Slab on grade floors or exposed slabs. So this could be a slab on grade home where there is no basement or crawl space, or it can be a walkout basement where you have a slab exposed to exterior conditions. So any slab that's within 12 inches of grade needs to be insulated to the specifications that are called out in the prescriptive tables. So essentially that's R15 at the slab edge and under the slab itself for a minimum of a total of 4 feet. So essentially it means, if you have a 4-inch slab, you got 4 inches here and then a minimum of 44 inches of insulation as a wing essentially run under the slab. There are some call outs where you can do R10 perimeter with 7.5 under the rest of slab, meaning that means you'd have to do R7.5 fully under the entire slab. So insulated slabs are only required if you have these conditions where it says an exposed slab to ambient conditions outside, or if it's a heated slab. The code does not require you to insulate under a slab if it is an unheated slab that is below grade. So if you have a standard 8-foot, basement and foundation, and it's just a rat slab down there, it's not heated. That slab does not require insulation under it per code to comply. From a building science standpoint, it's highly recommended that you would still put something underneath that slab because concrete's highly conductive and it can have a big impact on comfort and energy load to the house, as well as be a condensing surface in the summer months. But that's just a distinction to call out in the code. Crawl spaces. So if you have a crawl space as an alternative to insulating the floor system, if you have distribution in that crawl space as you see here, then foundation walls can be insulated or would need to be insulated in this circumstance to the same requirements as a basement would be. If there is just an excavation down here and exposed soils and dirt, then you need to put a vapor barrier over all exposed soils that's integrated into any insulation materials on the wall system as well. So walls, wood framed walls, above grade walls. The code's trying to make more account for moisture management in wall assemblies and how to retard moisture migration into framed assemblies as much as possible, while also accounting for ability for those walls to release moisture and dry out in some way as and if they do, and they will accumulate moisture. It's just physics here, folks. So to some extent, walls, closed cavity assemblies in general are going to load moisture to some extent during the heating season. And you want to keep that moisture loading as minimal as possible by putting in effective vapor retarding measures in those wall assemblies. But you also need to be sure that that moisture that does get into those walls has a mechanism for drying when the conditions allow for it and as the weather warms. So that drying can occur to the outside, or it can occur to the inside, or it can occur both ways, depending on the assembly that you decide to specify. So there's more detail called out in the code relating to this. This is where the code handbook has a lot of great content and info in it to help actually guide you in some of the assembly options that are available to achieve this. One of the more specific call outs is if you are doing an exterior insulation assembly where you're putting rigid foam board on the exterior of a wall, then essentially you're putting a vapor barrier on the exterior if you're using a foam insulation. So that wall is not going to be able to dry to the exterior, no matter what sort of Tyvek, Typar, other sort of WRB you put on the outside. The foam itself stands as a vapor barrier. So in those sorts of assemblies, you need to make sure that you have drying capacity to the inside of the building. So that's where we look at the different permeability, vapor permeability of different materials. So this specifically calls out options for using class 3 vapor retarders on the inside of a building, which means that you're allowing for drying potential to the inboard rather than the outboard side. And what we're really trying to aim at here is don't create a vapor barrier sandwich where you don't want to have a wall assembly where you have essentially a vapor barrier on the exterior and then a material on the inside of the wall on the inboard side that is also a vapor barrier. Because that is where you're going to trap moisture in a wall, and it's going to eventually just sit there and fester, and it's going to return the OSB back to its happy place, which is bark mulch, and the wall will start to deteriorate rapidly in those conditions. So you need, again, a drying mechanism at least one way, and there's certainly argument and methodology pushing in building science towards wall assemblies that can dry in both ways whenever possible. So just touch on some of the details of definitions here. Class 1 vapor barriers, these are, any material that has a vapor permeance of less than 0.1. So essentially something that's you're trying to keep moisture out is the intent of using materials such as this. So this is your standard classic 6 mil poly or aluminum facings, aluminum foils. Class 2 vapor barriers is a material that has a perm rating between 0.1 and 1 perm. So these are materials that do a pretty good job of keeping moisture vapor out, but they do have some capacity for moisture vapor to still then move through the material, breathe back through it, essentially. So craft facing on fiberglass has that capacity. XPS insulation, an inch thick or greater as well. And then class 3 vapor retarders are materials that have a perm rating of 1 to 10. Most WRBs, roll WRBs out there like Tyvek or Typar usually have a perm rating for comparison of about 15 to 20. So 30-pound roofing felt is historically been used as a good exterior WRB that is excellent at stopping bulk water and rain-driven water from getting to the sheathing behind it, while still allowing a lot of moisture vapor to pass through it from the wall assembly behind it. Latex paints, and there are specific vapor retarding latex paints available on the market as well that you use on the inside, that you're trying to prevent the bulk loading of moisture into the wall, but then that material will still allow drying inboard. Plywood as an alternative to OSB is also a much better, has much better vapor permeance than OSB does. A lot of OSBs really only have a permeance rating of like 1, where plywood, because it's dimensional lumber that's just sawn and laminated together, has a much higher permeance rating, so it can be considered sometimes as safer in an assembly than OSB. But all these things, it all depends on the overall interaction of all the materials together in the assembly. So it doesn't restrict you into what materials you can use. You just got to, again, as I said, make sure they all behave together well. And then finally, there are vapor variable membranes. So these are materials that will retard vapor flow under winter type conditions, but then they'll open up in warmer conditions and as the seasons change to allow for drying to occur inboard. Jumping into windows, we kind of touched on this already. We're talking about window U values for the entire building. You can use a weighted average of all the windows in the building to comply. So, if you need to meet 0.28 as your U value for a package, you can have 0.29 windows or even 0.30 windows in the building, just so long as all of the windows together as an aggregate average out to be 0.28 or lower. That you can exempt a certain square footage of 15 square feet of glass can be exempt from those U value requirements, and 24 square feet of exterior doors can be exempt from the U value requirements for doors. Next section here is on air leakage. I know we're coming up on time. I still have a few slides to go through here based on questions, but any questions that came up in that last section there quick? All right. Well, I'll keep running through here.
Yep, that sounds good. Thank you, Steve.
Yep. Another section to be, I'll go through these slides relatively quick, but this section of the code, R40241, and our section of R024 in general, covers specific details about how to detail the air barrier in the building. This is crucial to get an airtight envelope to meet the code requirements for air leakage, as well as also protect you from those interactions of moisture within assemblies and condensation and risk for mold and building degradation, the whole 9 yards. So really paying attention to the details in this section about how to properly specify air barriers within the building is worth paying attention to and getting into in more detail. The handbook has a lot of good detail on this as well, so I highly recommend taking the time to look through that. But essentially, in concept here, you want to have a properly detailed continuous air barrier in alignment with and in contact with the insulation materials that are going into the building assemblies. So anywhere there's a penetration in the building envelope, you need to make sure that's sealed up tight before you start adding insulation to that assembly. Attic spaces, recessed can lights, thankfully we're starting to see these go away because of LED fixtures not needing this huge little bump up into an open attic space. But things like this that exist in an attic, those need to be sealed up and made airtight. Wiring penetrations for wiring runs through wall top plates, plumbing vents, you name it, those sorts of things all need to be sealed up before you start insulating an attic space. A big one that's often historically overlooked is where you have a tub or shower wall abutting an exterior wall. You can't just put it on the wall cavity with open exposed fiberglass behind it, because what you are guaranteeing there is that you're going to have a rotten wall at some point down the road behind that tub enclosure, because you have nothing stopping warm, humid air from coming in contact and moving right through that fiberglass and getting to the cold sheathing behind it. So you need an air impermeable material between that tub surround and the insulation in the cavity behind it, unless you're using closed cell foam or a vapor impermeable insulation in the cavity behind it. So in the handbook, you'll see this drawing and an associated numerical table that's going to show you some of these crucial building envelope details that you should be paying attention to and understanding a good strategy for addressing as you're putting the building envelope together. And then finally, in the end of a project here, as the code requires now, is you're actually required now to have a third party come in, test the building envelope with the blower door to verify that you're not exceeding the 3 air changes per hour requirement in the code. Stretch code does require 2 ACH 50 or 2 air changes per hour, so it's a more stringent requirement for air leakage. Using the res check path or the HERS rating path does require that as well. So we do have a list of certified professionals who can do blower door testing on our website. So you can find people who can do that work for you. You know, I highly encourage builders to invest in blower door equipment because it's just as much of a tool in residential construction at this stage as is the table saw, circular saw, nail gun, compressor. You know, it's a way to verify that you're putting the building envelope together right, and not just to comply with code. I mean, that's a secondary benefit. It really is to cover your butt, make sure that you're doing the details right, so you're going to have a durable building assembly, and you're not putting yourself at risk of liability for damages in that building over time. Finally, a few other things to call out. Combustion safety is a big part of the code here now too, and I'll skip to the next slide first. So basically, any home compliant with the 2020 RBES is considered of unusually tight construction as defined by the fuel laws and fuel codes. So that means that any combustion equipment in a home needs to be closed combustion, sealed combustion. It's not relying on combustion air from inside the house to burn the fuel or to move the combustion gases up a chimney out of the house. So that's a general rule for requiring any combustion equipment in the building. And it does apply to wood burning equipment as well. So a fireplace or a wood stove in a home needs to have combustion air brought to the firebox, and it needs to, if it's a fireplace, have an airtight gasketed enclosure over the firebox. And this is there to keep smoke from coming into the house, you know, for adequate combustion air for burning the wood and for making sure that smoke comes out of the chimney and out of the house. So
Steve, we do have one question. I think it's from maybe Josh.
Okay, yep.
Yeah, this is for me. I think you made this clear, but just before the clarification, you can pick your package one, you can meet all the basic requirements, you can fill out the entire certification form, but if that blower door test isn't complete, you technically can't get that certification complete then, correct? You have to have a blower door test.
Correct.
That
is part of the compliance methodology at this point, is that you have to have that blower door testing done. One thing I'll call out quickly on that is a way you can gain a point in the code is to have a blower door test done before you put your drywall up as well. So if you have a blower door test done when you've basically finished detailing all of your air barriers and you're ready to kind of close it all up and finish the house out, having a blower door test done then will show you where you are in alignment for meeting the air leakage requirement at the end of the project. So it's a way to just verify that you're moving down the right path and troubleshoot anything that may come up as a result of doing the blower door tests. So just an option out there to consider.
Great. And we are just acknowledging time check. We are over by about 5 minutes. If you're able to stay, we certainly welcome you to join us for the remaining slides. So, but if you have to hop off, this is being recorded and we can make that available to you afterwards.
Great. Thanks, Bren. And so I'll just jump through this last section here real quick. R403 covers building systems, so we're talking mechanical equipment here. So this gets into the details of sizing, heating and cooling equipment for the house, specific requirements about installing mechanical ventilation, which is its own subject we could talk about, and we do have trainings that we do offer in regard to ventilation requirements for code. So this means that you do need to be providing mechanical ventilation for the house, not just venting building assemblies. So Section 403 covers those specific mechanical component details. And just briefly, electric resistance heating is prohibited, so you can't use generally electric resistance heat throughout a house. There are some exemptions if you're using air source heat pumps or other non-distributed heating equipment in the house to have limited resistance capacity in use, and that's covered under Section R4042. So finally, just to briefly touch on the mechanical ventilation requirements, this is, there's components called out in Chapter 3 as well as in Chapter 4, but every home needs to have a mechanically vented whole house ventilation system. So this means it can be exhaust only, using bath fans essentially, or it could be a balanced system where you're bringing in fresh air directly through a mechanical system as well as exhausting air out. But it needs to be a whole house system and it needs to be set up to run automatically. So just having bath fans in a house that a homeowner can turn on or off with the switch when they use the bathroom is not considered a whole house ventilation system. Those fans would need to be controlled automatically to provide the required ventilation rate throughout the day. So there's a prescriptive table way of complying with the ventilation requirements, or you can use some industry standards for actually doing more careful calculations based on the size of the house, number of bedrooms, number of occupants, building envelope air leakage rate, to get to you what you're looking for here, which is how much capacity of ventilation equipment do you need in the house. So this is the prescriptive way you can meet the ventilation requirements for the code. You know, you can use this table based on the number of bedrooms in the house. So let's say if you got a 3-bedroom house, you need to put in at least one fan that's rated at 100 CFM capacity on some sort of automated control, and you can comply with the code that way. But I'll leave you to consider if, one bath fan in a 3,000 square foot house is going to provide adequate whole house ventilation. I'd leave that up to you to decide, but you can comply with the code doing that. Alternatively, you can look at, a more distributed whole house system. So again, whole house or exhaust only systems, you're just sucking air out of the house and you're relying on leaks through the building shell, through the building envelope as your fresh air for the occupants. Whereas a balanced ventilation system, you're drawing in from the outside an equal amount of fresh air as you are exhausting air from within the house. Ventilation's there. These systems need to be in place for indoor air quality. And indoor air quality means removing contaminants from the house, pollutants from the house, and moisture from the house. Moisture is a big thing, and keeping relative humidity in check in a house is huge. And it's very hard to achieve that with exhaust-only systems. And with balanced systems as well, you're gaining the benefit of heat recovery. You're recovering the heat energy of the exhaust stream of air, and it's preheating the incoming fresh air coming into the house rather than just sucking warm air out of your house and expecting the building envelope to leak to get your fresh air requirement met. And you also get filtration of the incoming air as well, because the air handler itself has a filter in it, so you can improve the overall air quality through that filtration system as well. So you need to make sure that you're venting bathrooms adequately as well. There's minimum airflow requirements for bathrooms that need to be met on top of meeting the whole house ventilation requirement. But again, base code, balanced ventilation, heat recovery balanced ventilation is not required. You can use exhaust only, but if you are needing to meet stretch code, or if you're going to use res check or HERS rating as your path for compliance, you do need to start putting in those balanced ventilation systems. And where you are, there's minimum performance requirements for them. So the difference between an HRV and an ERV, HRV recovers the heat energy from the exhaust airstream, whereas an energy recovery ventilator is also going to recover the heat as well as a percentage of the humidity in the air as well. So there's debate back and forth and conversation to consider which one versus the other, but there's minimum efficiency requirements depending on the equipment that you choose to use. Bottom line is it needs to be automatically operated, so it's not at the homeowner's whim to run the ventilation system or not. This is especially crucial in the winter months. You can argue you can turn the ventilation system off in the summer if you got the house all opened up, but you definitely need an active and adequately sized and adequately functional ventilation system running in the winter, because condensation can happen and it can get bad, and it can get really bad if you're keeping these things, if allowing these things to happen unchecked. So thank you for sticking through this a little bit over time here. And again, we're here to help. That's our role, is code support, answering these questions, going into the building science in more detail with you. So certainly encourage you to reach out to us as you have questions. And do remember, our friends at the ICC are, this is copyrighted material from them, and go to the ICC site to get full detail on the code and the full language of it. So thank you. I appreciate y'all taking the time.
Yeah, thank you so much. I don't see any additional questions come in, but certainly reach out to Steve. Oh, I see some hands now.
Yeah, I'm happy to stick around. So
sure. So Josh has another question, and then Jay after.
Did you say happy to stick around?
Yeah.
Okay. All right. So I just have a couple quick ones, Steve.
Yep.
I appreciate you being able to stick around. So the code makes no distinction between what I sort of.
Josh, could you get a little bit closer to the mic? It's getting a little bit muffled.
Yeah. Sorry, can you hear me now clearly?
Yeah, that's much better. Thanks.
All right. So the code doesn't make a distinction between heated or unheated space. It's one or the other. So there's not a tempered space. And I'm kind of thinking specifically about a garage where somebody wants to put a modine heater in so that either their car doesn't freeze or they want to use it to tune skis. As soon as they introduce a heating element, that space is heated and has to meet all the requirements of the code. Is that a fair translation?
Yes. Yeah, so it's going to be a conditioned space. Yep.
And just conditioned for whatever it is, even if it's whatever, a connector that they just want to keep above 50 degrees. That really doesn't, there's no such thing as a tempered space. It's either heated or it's not.
Yes.
Okay. My only other question, actually, you answered all the other ones I had so far, but is the res check software, has that changed at all in any degree? Are you confident, somebody like myself can fill that thing out pretty simply and work their way through it, or is that going to require some additional help, you think, when we get into it?
If you're used to using it, it's still the same format, same functionality. The big difference, though, is that the 2020 RBES is not supported in the desktop version of it anymore. You have to use their web-based version of it. So you just have to create an account and sign in through.
It's on the cloud now. We can't put it on our desktop, you mean?
Right. Yeah, but it's going to save all of your project data and everything through that portal and through that access. So it has been updated to all of the relevant 2020 performance requirements. We are seeing some things that are going to need some tweaking that are cropping up as people are starting to use it. Like there's a few things that came up last week that we're working with PNNL, who is the developer who runs or owns ResCheck essentially. So we're working with them to make those adjustments as needed, but it has been fully brought up to the 2020 code requirement.
Okay. That's all I had for now. I really appreciate it. So,
all right. Yeah,
so I guess I will ask one other question.
Sure.
I don't really need to look at the stretch code unless, like you said, it's either an Act 250 or required, or if a client specifically wants to push the limits. But other than that, I can kind of just stick with the base packages for most constructions down by where I'm at, right?
Yeah, I mean, base code's, minimum. So of what you need to build off of. And the reason why there's this point system in the code now is to allow for the code to remain somewhat static in its base requirements for moving forward here, and allow for flexibility about how to get better performing building envelopes, because you have that flexibility with the points. So so there's ways to, up the ante a little bit. But I mean, a code built house right now, based on the 2020 RBES is a pretty good outcome. I mean, it's a pretty
agreed.
efficient home. So, and really the bottom line for me on any of this is it's all based on sound building science. So it's not only just the energy performance and efficiency you get out of it, but it's holistic durability as well.
I'm with you. Nice to see you again, by the way.
Yeah, you too. Thanks.
Thanks so much. Jay, you have questions?
Yeah, this is probably a pretty quick one. You referenced the handbook a couple of times. Where do we get it?
That is on the Department of Public Services website, on their energy efficiency page under RBES. It's also available on our website. Bryn?
I'm gonna jump in and help you out with that one. So a PDF, a digital copy, is available, and I'm gonna drop a link into the chat in a second to help you find it quickly. And if you want a hard copy, I'll actually also add my email address in here. So if you want to just send me a quick email with your mailing address, I can make sure we get you a copy.
All right, great, thank you.
You betcha. And I think that's it for questions. So I'm just gonna find the code link, code support website, and then add that in. But thank you again for joining today, and we certainly are here for any and all questions that you have as you're out implementing the code work. So thank you so much.
Thank you all. Take care.
Thanks.